we are going to do the second page, okay, of yesterday's post. This is 9.2, Waves at Media Boundaries, okay? All right, so what is a media boundary? Well, media is really kind of short for medium, if you want to think of it like that, okay? And we've talked, I don't know if we have talked about sound as a wave, because that's what this is about, sound and waves. Most waves need to have a medium, okay, with the exception of electromagnetic waves or light. So what happens is waves behave differently when they're in different mediums, which we did speak about with sound, okay, because we talked about how different densities affect it. So we're going to look and see how the mediums change a pulse, okay? So really, a media boundary is a point or place where the type of medium changes. And it could be a complete change of medium, or it could be, so it could be water, but then the depth of the water changes. Okay, or it could be like from air to water. It doesn't need to be a new medium, it just means some characteristic of the medium changes. Characteristic. Oh, characteristic. Okay, some characteristic of the medium changes. Okay, so there's a change. All right, so in terms of a pulse. So yesterday I showed you a quick video. I'm going to, or it was a demo program. I couldn't find, I'll look harder and see if I can find and make a little video of this, all right? It's not a perfect one, but I can show you. So what I'm talking about is here's a positive pulse. It's coming. And I don't know if you can see on your paper if it came out, but it's a little bit shaded here. So we're going to talk about free end and fixed end. What is that? Okay, so a free end means this end is free to move. It's not attached to anything. And we're going to talk about a fixed end. So let's say I'm holding a spring. Okay, I'm holding here. I send a pulse, boom, and this pulse goes down. Here I would just have one and I would just send it. Nothing's holding the end. All right, and I can show that with a FET demo. I just realized that one is good for that. All right, so here we have a pulse. It's a positive pulse. Its amplitude is A if you want to make a comment about that, because we're not losing any energy in here, because I don't know if you can see. So this is taken, snipped out of your textbook. If you can't print this, all you're going to do is you're going to draw a blip, okay, and you can see which direction the energy is traveling in, or the pulse, because here we have an arrow. So it's traveling this way, it reflects off and goes to the left. So what's happening? Let's examine our pulses. They are both positive, okay, and they both have the same amplitude. Now in reality, there might be some energy loss, but we're showing no energy loss, and the pulse comes back in the same direction. So it gets reflected positive. So a positive pulse, okay, positive meaning above. That's what a positive pulse is, reflected with no energy loss, okay, as a positive pulse. Okay, so it means it has a positive amplitude, it comes back as a positive amplitude. Like I said, I'll try and show you a demo on that on FET, okay? And I know you're like, oh, but how is that a medium boundary? A media boundary? Well, I mean, the media ends, so essentially you'd have a spring or a string and it's reflecting off of nothing. All right, now it's completely different, all right, when we have a fixed end, okay? And I said pretty much before that sound and waves, we can kind of forget everything that we did in the other units, but it actually does come into play every once in a while. Not necessarily math, but the theory. And I'll explain to you why this actually has to do with Newton's third law. Okay, because when I show the video, you're going to see the amplitude for a moment actually go double. And that has to do with the principle of superposition. Because at that point, the pulse the incident pulse and the reflected pulse are adding at this moment in time, and we actually get double the amplitude. All right. And that does not happen on a fixed end. But you'll notice on the fixed end what happens here. All right. And also in the video, I'll show you what happens with a negative pulse. If this came negative, okay, and if you want to have like the media boundary, how do you think that would get reflected? It would also get reflected and not flip, okay, as a negative pulse. So when it reflected back, it'd go like this and back, okay, as a negative pulse. And this would be this is my rest position, okay? So now a fixed end is different. This end right here is held, all right? So what's going to happen is as this pulse comes, this is fixed. So as the string tries to apply a force upward, because this is, right, all these particles, as it comes along, these particles are all moving up, and these ones are actually moving down. I always think of myself as floating on like a water wave. So this tries to apply a force up, but Newton's third law says, no, you apply a force up on me, I'm going to apply a force down on you. So what happens is every single time or point when the energy and the medium is meeting at this point, the boundary applies a force downwards. So this pulse actually gets reflected in the opposite direction, and it will travel on. And yes, so this is amplitude, and so now this is, we still name it as amplitude, but it comes back as a negative pulse. So a positive pulse is reflected, as a negative pulse in the opposite direction. So if it was fixed and I threw it in as a negative, it would come back as a positive. All right. So that's what you need to know. Now, why is this important? Well, it's going to be important when we talk about standing waves. So it's just something I want you to keep in the back of your head. It also comes into play in grade 12 physics, because in grade 12 physics, you'll do waves, light as a wave. Okay, and you're going to do the wave properties of light. So this is important when we talk about the interference of light. And that's the whole unit in grade 12. Now, what also happens, okay, is sometimes what we have is the medium changes. So here we had like a medium and no medium, all right? But here, the medium can change. And what happens is we get partial reflection, partial transmission. And maybe this sounds familiar. I almost said refraction, because in grade 10, when you did light, your teacher might have shown you, and I don't know if you guys noticed, when you had your semicircular prisms, I always point out when the ray of light comes in, some of it gets refracted, but there's always some light gets reflected. So this is partial refraction, partial reflection, and it's really what's happening here. You get partial reflection and partial transmission. And what happens is it depends on the density of the medium of one relative to the other. How does the pulse come back? Does it come back as positive or negative? So when there's a change in density of the medium, the speed of the wave changes, and this affects how the energy of the wave gets transmitted and reflected. So here, if I have a slow medium and I have a faster medium, if I have a positive pulse coming, some of it will get reflected. It gets reflected in the same direction. So a positive pulse gets a positive reflection. It also has a positive transmission. And if I could add these two amplitudes up, these two amplitudes, if I want to call it A and A, or let's go A and B, these don't have to necessarily be the same. In this picture they are, okay? So what would happen is this A plus this B equals this amplitude. So what we get is we get partial positive reflection and transmission. All right, and again, this is important in grade 12 physics with light because we talk about mediums changing, okay? So now if we go from a faster medium to a slower medium, this acts somewhat like a fixed end because this medium is harder to move. So when it meets here, this applies a bigger force, so the reflection comes back as a negative, but the transmission goes through as a positive pulse. So if I have a positive pulse, so we get a partial negative reflection, okay, or it gets flipped, okay, and partial transmission. Okay, so here we get a partial, so this is no flip. All right, and that's really what you need to know. This comes into play, like I said, when we do maybe principle of superposition. Not necessarily this one, but the one above. Okay, now in your note, it says explain how the principle of superposition is an application of conservation energy. Read about standing waves. This is a special case of principle of superposition. So what I've been showing you is just pulses, individual pulses. But what we want to do is I want to show you a whole bunch of pulses, which essentially is a wave. And when all those pulses add up and reflect and interact with one another, they produce standing waves. And I'm going to show you that next, okay?